The following is a conversation with Nick van Remortel, professor of physics at the University of Antwerp. His research span elementary particle physics, radiation detectors, gravitational waves. He is part of the following projects: the compact muon solenoid experiments at the Large Hadron Collider at CERN, solid neutrino experiment at the SCK-CEN in Belgium, and he is part of the Einstein Telescope project. I hope you will enjoy the conversation. This is Back to the Stone Age. Nick, what is the cosmic microwave background radiation?
So the cosmic microwave background, or CMB as it abbreviated by most scientists, is in fact an isotropic form of radiation, which is to first order independent of the direction of observation. It has a mean wavelength of roughly 2 millimeters, and it is interpreted that it corresponds to a temperature of the universe of 2.7 Kelvin. So 2.7 Kelvin corresponds roughly to minus 250 degrees below zero in Celsius. So the CMB was discovered in 1964, essentially by a team of scientists that were not searching for the CMB. It was discovered by accident. It led to the Nobel Prize in 1978 for Penzias and Wilson, the two guys that discovered it. And it provides a major break. To me, it's one of the most significant scientific breakthroughs in modern physics. So the consequence of the discovery of the CMB basically was that it overthrew a couple of hypotheses concerning the origin and the state of the universe. So it overthrew the hypothesis that the universe was in a steady state, that it was that it had always existed, that it was never changing, that there was no preferred direction and place in the history, but in the universe, but also no preferred time. And instead, it favored the hypothesis of the Big Bang, the hypothesis that the universe was created roughly 14 billion years ago from a very hot, dense state of matter that since then has been expanding and cooling down. And so the CMB consists of light, or in physics, they are called photons, particles of light, that dominated the energy density of the universe when it was very young, in its earliest stages, when the universe was quite hot. And these photons, they were in thermal equilibrium with the matter, with electrons and other elementary particles that then later condensed into protons and neutrons to actually form the lightest elements of the periodic table, like hydrogen and helium. And at some point in time, roughly when the universe was 380,000 years old, the temperature of the universe had dropped sufficiently low temperatures, roughly 3,000 degrees, which made that the photons did not have a sufficient energy anymore at that temperature to dissociate or to ionize the hydrogen atom in the hydrogen atoms in this primordial plasma. And at that point, the photons were free to travel for very long distances without interacting much, without being absorbed or scattered, without changing directions. And since the universe was at that stage in thermal equilibrium, the spectrum of these photons, so the distribution of wavelengths of this light, of the CMB, has a very specific shape that was first discovered and described by a guy called Max Planck, which is one of the pioneers of the quantum era. And so this Planck spectrum, so this distribution of wavelength of photons, is dependent on only one quantity, a macroscopic quantity, which is the temperature. And so this spectrum is called the blackbody spectrum. Now, as the universe further expanded and cooled down, the photon energy density or their temperature decreased, and also the wavelength of the photons increased, got stretched out. But the fact is that these two effects are present at the same time implies that the spectrum, this Planck spectrum or black body spectrum, retains the same shape throughout the whole history of the universe. And therefore, it was predicted that given the estimation of the expansion rate of the universe as measured by Hubble, the photon wavelengths must have stretched in such a way that their black body spectrum would now correspond to an equivalent temperature of 3 Kelvin. This was a firm prediction at the time, before the CMB was actually measured. And now the big success of the first measurement of the CMB is that indeed they measured a wavelength, range of wavelengths of these photons that correspond to a temperature of roughly 3 Kelvin, 3 degrees above absolute zero. So this was a major triumph of very simple assumptions on cosmology, the creation of the universe, and the subsequent expansion of the universe.
Okay, you gave a lot of details and also values, but for example, when we saw the first picture of a black hole, for example, I could precisely picture in my head, in my mind, what this astrophysical object is. Now, what I ask you is, how, when you think about the CMB, how do you picture this radiation in your mind? How do you see it?
Well, to characterize it for the layman, I would say that the cosmic microwave background is the oldest light from the universe that we can observe today. Therefore, the picture that we have taken from the cosmic microwave background is the picture that looks the furthest distance that you can possibly observe with any form of electromagnetic radiation in the universe. So, okay, it provides a snapshot of the universe when it was relatively young, 380,000 years old, but encoded in the specific patterns of this picture is a lot of information that pertains to the state of the universe when it was much younger. So from looking at these pictures, from analyzing these pictures, we can deduce a lot of the early physics that happened in the first few seconds of the universe, and we can test these theories by calculating how this has translated in the patterns of temperature fluctuations we see now in the cosmic microwave background. So yeah, there are a couple. I mean, the amount of information that is contained in the CMB is enormous in terms of the physics you can deduce from it. So the scenario that is now currently accepted by all mainstream physicists is that in the Big Bang model, the universe starts out from a very hot and dense initial state, and subsequently it can expand and it cools down. And as I said, the light in the early universe was actually dominating in those earliest stages the total energy content of the universe. So you can describe the early universe basically as a volume of gas that basically consists of light. And therefore, you can compute how this universe can expand, and then at some point how it cools down, and how this light then decouples and travels freely without interacting much further with the rest of the universe. And some of these things that we have learned from it are quite remarkable. We know, for example, that when the light decoupled from this hot plasma, The universe length scale, so the actual stretching of the space-time of the universe, was of the order of 1,000 times smaller than the current distance scales in the universe, which means that if you would take a volume, this volume would be roughly a million times smaller. And so another important thing that you can deduce from it is what was the amount of light compared to the amount of nuclear matter present in the universe at that time. And it appears that if you do the calculations, there were roughly 1 billion times more photons, more light particles than nuclear particles in the universe. And this ratio has remained constant since the photons of the CMB decoupled from the matter. Now, it is also known that only at the time when this light decoupled from the nuclear matter, that only at that moment the nuclear matter could clump together gravitationally to form the first galaxies and the first, and that would finally result in the large-scale structures that we currently observe in the universe. The big problem is that if you calculate what kind of structures this matter can form, if it's only allowed to cluster at that time, is that given the ordinary matter, neutrons and protons, is that there is way too few matter available to create a very large structures of galaxy clusters that we observe in the universe today. So one of the solutions to that problem is provided by the notion of dark matter. So simply the simple measurement of the temperature of the cosmic microwave background give already a clear indication that we need a huge amount of dark matter, a matter that does not interact with photons, that would allow to cluster already at a much earlier stage, which is absolutely necessary to explain the current large-scale structures we see in the universe today. So that's one additional essential form of information. Then another thing is that once the whole spectrum of the CMB was measured, so you need to measure at different wavelengths to see what the intensity of the light is at each of these wavelengths. It corresponds to a perfect Planck-like black body spectrum. And its temperature is now confirmed to be 2.73 something Kelvin. It's measured to a high degree of accuracy. It's measured to the microkelvin level precision. Now, one of the amazing surprises is that indeed these temperatures do not change at the level of 1 in 100,000. So the fact that the temperature of the universe is so uniform at such large scale is a very big surprise. And the reason for that is that at these earlier stages, when the universe was very small, the maximum distance that photons these light particles were allowed to travel was a fixed distance of the order of 14 million parsecs, of the order of, let's say, 50 million light years. If you translate this in the angular distance, you can see this now in the sky. This corresponds to roughly 1 degree of angular distance. The fact that you see such a uniformity of the CMB temperature at distances, at angles larger than 1 degree, is a huge surprise, because this light has never been in contact with one another. So there is no reason why it should be at the same wavelength or at the same temperature at that level of precision. And therefore, again, you need an additional explanation to explain why this can be. And one of the hypotheses that supports this is the idea of inflation. The fact that in the earliest fractions, the tiniest fractions of a second after the Big Bang, the universe, the space itself expanded at a rate faster than the speed of light, allows for the fact that all these perturbations in the energy density or the temperature of the universe are smoothed out. Inflation also explains another aspect which we observe in the CMB by looking at the angular distances between the hottest and the coldest spots in the CMB map. You can deduce the overall geometry of the universe or the curvature of the universe. Now, the calculations I explained you before indicate that the angular distance between the hottest and the coldest spots in this CMB map should be roughly 1 degree apart. They should be separated by one degree of angle. And that is if the total geometry, the global geometry of space and time is flat in the universe. If the universe would be curved like a ball, like a sphere, so positive curvature, these angles would appear to be bigger. If, on the other hand, another possibility, the curvature of the universe would be negative, so the shape of the universe would be like a horse saddle like shape, then these angles would be smaller. So measuring exactly the angle at which the minimum and maximum variations in temperature occur on the sky gives you also a measure of the curvature of the flatness of the universe. And it appears that the universe is, to a very good approximation, extremely flat. Now, if you do not have inflation, you need to fine-tune a lot of parameters, a lot of conditions in the beginning of the universe to make these two things happen at the same time. A flat universe and a homogeneous and isotropically an isotropic temperature at the level of 1 in 10,000. Now, inflation accounts for these two effects. So what the measurement of the CMB has done is it provides us a number for the ratio of the amount of photons over neutrons and protons. Then it creates a puzzle by saying that the amount of protons and neutrons at that time could not clump sufficiently fast to provide for the largest structures we currently observe in the universe. Thus, we need dark matter. And secondly, the uniformity of the temperature and the angular distance of the fluctuations we see in this temperature imply the need for a special kind of physics to have occurred very early in the universe, which is called inflation. So it supports quite some spectacular theories from which otherwise we would have very little information.
Okay. I wanted to ask you, does the geometry of the universe can change and evolve throughout the history of the universe?
Yes, and it has. It most likely has. So yeah, it all depends. Essentially, the whole of cosmology can be characterized by 3 main parameters. This length scale, so the way the universe expands or contracts over time, the overall curvature of the universe, and then the total energy density in the universe. And they are all 3 connected through a set of essentially 3 main equations of cosmology. And so the big aim of the game in observational cosmology is, of course, to make observations that determine the values of these 3 parameters through the whole history of the universe. And yeah, many solutions exist. The current global picture is that the curvature of the universe in its very early stages was positive and relatively large. Then, due to the inflation, the universe has flattened out. In the first stages, the energy density of the universe was dominated by photons. In the intermediate stages, when the universe was a couple of billion years old, then the matter content of the universe started to dominate the overall shape and the expansion rate of the universe. And in the future, and we see an onset of this already happening now, is actually another form of energy called dark energy, which determines the overall expansion rate and the curvature of the universe. So there is the universe has constantly been evolving, both in shape, in geometry, and in in, let's say, and in expansion, in rate of expansion.
Okay, so can you correct me, please, if I am wrong in having this picture in mind? So basically, at the what we call the beginning, if beginning makes any sense, we could imagine the universe sort of as a very curled up ball or a very curled up space because
Yep.
all the matter that was there was very packed up together, and thus the gravitation uh, and thus the space-time curvature at that time was very high. And as the expansion sets in and progresses, then this gravitational attraction and thus this curvature slightly unfolds. So in my mind, if I think about it, it seems to be as a sort of as a ball which gradually unfolds into a plane. Now, of course, this is very approximate because we are talking about 4 dimension. But is that a correct
Yeah,
thing?
it's a bit naive, and it's a common misconception of people who have not studied cosmology, is that most people assume that the universe was per definition small at very early times when it was born. And this does not need to be the case. In fact, there is also an open question whether the present universe is infinite or not in size. Right? We know that the universe is most definitely larger than the universe we can observe up to this date. The simple intuitive reasoning is that the light that we can receive, we can see now, is roughly 14 billion years old. But the light that we will see tomorrow will come from a region that will be 4 billion years plus 1 day older, and so on and so on. So every day we are in principle capable of seeing a slightly larger patch of the universe. Okay. So the fact that we have a limited view on the universe is almost intuitively clear. Now, what is the final size of the universe? That is an open question, and that again depends on these certain of these essential cosmological parameters. The only thing we currently know is that the size of the universe is larger than the present so-called Hubble scale, which is of the order of 3,000 million parsecs in size.
Which
Now,
are approximately how many billion of light years?
a parsec is 3 point something light years, so it would be of the order of 10 billion light years.
Okay.
So how much we can see depends again on the shape, the curvature of the universe, and also on the fact by how much has the universe expanded since creation. But so if there is the option, the possibility that the present universe is infinite, it means that it was already infinite at the time that the Big Bang occurred. So Big Bang does not necessarily imply that the universe was infinitesimally, how do you call it, infinitesimally small at the time of creation. It could have been infinitely large. The essential thing is that the energy density at the Big Bang was extremely high, tending towards infinity, and that the temperature was extremely hot. But the size itself, we have basically no constraints about.
And what does it mean that you can have an infinitely large universe where the energy density is infinite?
It means that all the matter and radiation must be packed extremely close together in space. A density is the amount of matter or energy per unit of space. And so if space and time stretches, then this density dilutes, unless you would create constantly new matter and energy, which is in contradiction with all the current astrophysical observations. But of course, if you wind back the movie, then you say if these distances shrink and shrink and shrink, all these this energy is packed in tinier and tinier volumes of space. And so the energy density increases dramatically. And of course, we know as infinities most likely do not exist in actual physics, is that this calculation breaks down at the levels of a scale called the Planck scale or the Planck time, where we know that we cannot simply describe anymore the evolution and the condition of the universe by general relativity alone, but that we need an over-encompassing theory that includes quantum mechanics together with gravity.
Okay, so basically when I was reading and preparing this conversation, I have seen the data. I don't remember according to which theoretical framework that, as you said, the universe, the actual size of the universe is certainly bigger than the observable universe. And if anything, it could be of the size of 200 or 250 times bigger than the current size of the universe. You, however, mentioned that, of course, there is an open question in physics whether the actual size of the universe is infinite. What does an infinite size of the universe mean to your finite brain?
It doesn't mean anything. I mean, it's not per definition stranger than a finite size universe. I mean, in practice, it would simply mean that
there is no ending.
There is no ending. It would stretch out forever. So yeah. Why would this solution be preferred instead of or not preferred? Why would this hypothesis be dismissed by saying that the universe would stop? To me, it's weirder to say that the universe would stop somewhere rather than saying that it's infinite.
Okay. Sometimes when I think about infinity, especially related to the size of the universe, I believe that infinity could be more well understood as a concept if we do take okay, because when we talk about finiteness or infiniteness, we talk about size, so distances. But my thought was, okay, what if the concept of infinity regarding taking into account only the dimensions of size of space is sort of ill-posed, is not really meaningless. The concept of infinity start making sense when we take into account also the dimension of time. Because as we said, an infinite universe would have no ending. It means that if you keep on traveling in space, but also in time, then you would reach no end. So do you believe that sort of the concept of the infinite is probably at its early stages for us to wrap our head around a possibly infinite universe?
Yeah, I agree with you. It's a good way of putting it. And as I said, there are still quite some uncertainties on that statement. There is the other aspect whether the universe is bound or unbound. If it has a net curvature, it can be curved like a ball. Then it's bound. If not, then it's unbound. So there are many variations possible. But what we currently know that is in the present state, the universe is quasi-flat, or we are seeing such a small patch on such a huge ball, four-dimensional hypersphere, that it's almost impossible to say with such a large radius that it's almost that is nearly impossible to distinguish whether we are on a flat space or just a small patch on an extremely large curved surface. And that the other statement that we can make about it is that the universe has expanded throughout its history. In the first very minute fractions of a second, it expanded exponentially fast. then the expansion has been more or less linear, and then it has flattened out when the matter content of the universe starts to take over. It tends to slow down the expansion because matter basically implies that the universe wants to stay together. And so at some point, we kind of flattened out, and the expansion of the universe basically stopped. And then at some point, when this dark energy component takes over in the evolution of the history, then the universe starts expanding again. And apparently, we are now at this transition point where in the recent history of the universe started to expand again with an accelerated rate.
Okay, now there is a question which is probably very unanswerable, I would say. But if we say that the universe might be infinite, or at least let's say that the universe is finite and bounded, so as you said, as a sphere, and we know that this sort of a sphere, through observation, this sphere is expanding. But what is this sphere expanding into?
That's also a very common question, but it is also a wrong question in the sense that there is nothing in which space and time expand or stretch. It is the space and time that expands by itself, which means that there is no point in the universe where you can say, okay, there is no preferred direction or no preferred position where you can say everything started here in this point and then it started to expand from here on out. Everything, everywhere expanded, what we currently assume, with the same rate, with the same velocity, and in the same way.
Okay, if you have to bet your money, a lot of money, on whether the universe is infinite or finite and bounded or unbounded, what would you say?
It's a game I don't like to play because I think that in physics, physics does not really depend on what you believe. Physics depends on facts and on a correct interpretation of facts. So currently, we cannot say we're extremely certain. We cannot answer these questions completely with 100% certainty. So I just stated the things we can say, and whether the universe is then infinite or not is an open speculation for which which we probably can never answer.
Let's hope we can. Also, we're just talking about millions and billions of light years, so extremely large numbers. Now, on the other side, we have extremely small numbers when we take into account quantum mechanics. But let us just stick with the big numbers of typical of cosmology. Does it make sense in your head when you are talking about billions and billions of light years in distance? Because sometimes when I am reading books or I am watching videos and I hear people talking about these gargantuan distances, I feel like they are not understating them, but they are talking about them as if they were nothing. But do you actually, in your mind, again, in your very finite mind, wrap your head around the enormity, the giganticness of these distances?
No, it's very difficult, both in the macroscopic world of physics, of let's say cosmology, and in the microscopic world of quantum mechanics. For a physicist, it's very well. First of all, for a non-physicist, it's extremely difficult to visualize the concepts that we talk about, because we live in a world where we can basically just see wavelengths, light in the visible light spectrum. So from a couple of microns to a couple of tens of microns. Our hearing, our senses, our hearing, for example, is also only sensitive to a narrow frequency bandwidth and so on. Our lifespan is also of the order of, let's say, 100 years, if you are lucky. So all the experience we have from day to day gives us only a very limited view on our surroundings. And for all the other observations, we need to rely on measurements with some form of electronic apparatus. And the deeper you dive into the measurements of the microcosms and in the measurements of the macrocosms, the more extreme these complicated these measurement devices become, and also the more complicated it becomes to interpret the results and to translate them to day-to-day concepts. For example, in particle physics, we talk about an electron and about a quark and things like that. But it's very difficult to imagine in your mind how an electron would look like or how a quark would look like, let alone how it behaves. And the same goes for these ultra large distances at cosmological scales. The amount of stars that are present in galaxies and the amount of galaxies we have in the universe. I mean, these are mind-boggling figures, which are extremely difficult to imagine. And I think the part of the education of a physicist is, first of all, to learn to accept, to let go, that you cannot compare each of these concepts to day-to-day life events or objects. That's one thing. That at some point you basically have to rely on the mathematics. And that secondly, if possible, wherever possible, you need to anyway learn to develop some kind of a physical intuition. Okay, it makes sense or it doesn't make sense, to make a conclusion of whether your calculations or your measurements are good or not. And this, the development of this physical intuition, and to say, okay, this is possible, this is not possible, is something that a physicist develops during his or her education, academic training. And I must say that some of the brightest physicists have developed theories or have defined experiments that are so clever, basically based on the fact that I have such a nice and fine intuition, a physical intuition, to see what could be measured under what circumstances and what kind of technology and what kind of precision you need. And these are the brightest physicists that can basically sit with you at a terrace and take a napkin and say, let's try to think of an experiment that could measure this and this and this. And then in the end, yeah, you have the basic numbers of what you can measure with what sensitivity and how you would need to construct a machine or an instrument to do it. But these are quite rare physicists. They are the best typically.
Can I ask you, ChatGPT knows a lot of things. So if whenever I talk with ChatGPT, I have the sensation that it knows a lot of stuff, everything. However, it is somewhat, not somewhat, it is a lot limited in coming up, of course, with a new physical and mathematical explanation of the world. It's very limited in coming up with experiments that lead us to get closer to the truth of our reality. So how special and what is different in those human beings, as you described, in those physicists who were able to invent a way of looking at things which turned out to be the proper way to look at things?
Yeah, I think when it comes to scientific questions, ChatGPT is basically an algorithm that can condense the most commonly appearing facts or physical statements that it can find on the internet. Now, breakthroughs in physics happen by intelligent human beings that are able to, that first of all are knowledgeable enough about all the scientific facts that exist, but that can also connect. So what distinguishes AI algorithms, current AI algorithms such as ChatGPT, from human beings is that human beings can go beyond simply collecting facts and summarizing facts from the internet. But the added value is that they can see connections or relations or patterns between seemingly unrelated facts. That's one important thing. That they can provide context. And that the second part is that they have, the experts have developed this kind of physical intuition that give you an idea of, in this whole pattern that I'm synthesizing from all these scientific facts, there appear to be either inconsistencies or holes of information that need to be filled in. And for this, I can design a new experiment, or for this, I can develop a new theory. And it's this kind of filling the missing blanks and connecting the patterns from seemingly completely different sources of information is something that AI algorithms still have difficulties in doing.
Okay. Well, these brilliant physicists that we were talking about are the physicists who came up with what is called the most brilliant theory of our of the physical universe, which is the Standard Model. I would like to ask you, the Standard Model, we know that describes a gigantic amount of physical events, and we described these physical events with a huge accuracy. However, we do still miss some puzzles, so we do still miss some pieces, some phenomena to describe. So how far is the Standard Model actually is from being a theory of everything, and is it in principle even possible to have a theory of everything?
Yeah. So particle physics, and this is also one of the reasons why I specialized in the first place after graduating in physics to specialize as a particle physicist, is that I think particle physics is a very materialistic and reductionistic way of looking at nature and looking at the universe. So the philosophy is that by analyzing the fundamental constituents or the building blocks of matter, and by accurately describing how these elementary building blocks interact, you can in principle predict the whole all complex phenomena that are present in the current universe. You can explain chemistry, biology, and whatever. It's not the most effective way to do it, but in principle, it should be possible. And secondly, by knowing what the primary constituents of the universe are and the governing rules between them, you could predict let's say, derive something on the early conditions of the universe, and from that predicts its evolution, so the current state, and also its future. And remarkably, this has worked quite well in certain areas. We can, for example, predict the amount of light chemical elements that were produced in the universe, like hydrogen, helium, etc., lithium, etc. And that is a remarkable feat, that you can predict this from these elementary building blocks and the evolution of the universe, etc., etc. So on the other hand, we have also learned that this so-called standard model is quite primitive, because we know that from cosmological observation, astrophysical observations, we need quite a large amount of dark matter. Roughly 25% of the total energy content of the universe should consist of dark matter. 70% should consist of dark energy, and then only 5% should consist of all the, let's say, what we call the baryonic matter that we see in stars, galaxies, etc., etc. And so The standard model, in effect, therefore describes only roughly 5% of the total matter and energy content of the universe.
That's not a great achievement.
That's in itself not a spectacular achievement. So it is humbling also at the same time. The beauty of the standard model, however, is that the theory is mathematically very elegant. It is based on the notion of symmetry in nature, and symmetry in nature provides tremendous amount of beauty and variety in nature, even though the actual rules of the game in nature can be quite simple. Symmetries, and often also the breaking of symmetries in nature, can provide some of the most beautiful patterns and some of the most complex phenomena that we can observe up today. So playing with mathematical symmetry is an extremely satisfying game. Now, one of the most remarkable consequences of symmetries in nature is that if you impose in the theory of the standard model these symmetries, abstract symmetries on space and time of nature, you can derive the properties of the interactions between these fundamental building blocks, and at the same time, you predict the existence of fields or force carriers. So to give an example, in electromagnetism, the theory that describes the interactions between electric charges, that can be described by a so-called relativistic quantum field theory, in which a couple of these symmetries are built in a priori. And as a consequence of these symmetries, it gives you two important results, namely that there must exist a field that is responsible for transmitting the electromagnetic force between charges. And this field corresponds to light, is the field of the photon. And it automatically rolls out of the theory without you having it put in from the start. So it tells you that the electromagnetic force is transmitted by a force carrier called a photon, which we now identify as light. So that's a remarkable aspect. And this same phenomena can be extended in the theory of the other forces of nature, namely the weak and the strong nuclear force. So by imposing these symmetries, you can make predictions of phenomena that are so remarkable that, first of all, you did not have to put them in by hand to start with. You can go and measure them in experiments, and you measure all the properties of these predictions to an astounding accuracy.
However, you said that we are missing that, let's say, for the 5% of matter content of the universe, the accuracy of predictions is astounding, which is a great achievement indeed. However, you said that indeed we are missing 90%, approximately 90% of matter and energy content in the universe, which is dark matter and dark energy. Now, these things, dark matter and dark energy, have been puzzling scientists and physicists for a long time, sort of a relatively long time now. And now I would like to ask you, do you believe that the changes in our physical theories and in our understanding of the working of the world would have to be drastic compared to the way we look at the world now and compared to our understanding or the physical theories, or is it more technological, let's say, an engineering problem?
No, first of all, I don't think that, well, to start with, the problem with dark matter and dark energy is that these two phenomena are only needed when you study the universe at relatively large scales. If we were ignorant about the universe and would only look at any experiment you can do in a laboratory on Earth, there would be no indication of a need for dark matter and dark energy, and the standard model would be a fantastic theory that would describe basically everything we see in nature. So there is a problem that is dark energy and dark matter are only needed at the scale of the universe, where basically gravity is the dominant force. While all the experiments we do in elementary particle physics at accelerators are conditions in which gravity does not play a role at all. So that creates a problem, but also let's say a dispersity between these two worlds, between these two laboratoria, the universe and itself, which is dominated by gravity, and particle physics experiment in which gravity is negligible. So you can see from a technical point of view, it is very difficult to construct experiments either in the universe or here in the laboratory, where both the effects of gravity and the effects of quantum mechanics become equally important. And so at the moment, we can only think of two possible conditions where these two interactions become equally important. That is in the center of black holes or in the conditions that were present during the very early stages after the Big Bang. And therefore, our only current experimental hope to study either the failure of the theory of gravity and of the standard model, and how to join the two together would be primarily by looking at these two types of physical systems. Of course, at the same time, knowing that, for example, the standard model is an excellent theory, but it should break down at regimes of very high energy scales or very small distance scales. We try to create more powerful accelerators to see, to detect deviations from the predictions of the standard model. That's one strategy. And on the other hand, we also try to measure extremely rare processes in nature to such high precision that if there would be other aspects of that go beyond the standard model, that we would detect indirectly the impact of these deviations of the standard model on our measurements. So these are the two strategies to, first of all, look for a breakdown of the predictions of the standard model, and secondly, also look for a breakdown of the predictions of general relativity. And that's why I think particle physics and now recently also the domain of gravitational wave science, for example, are the two domains which are really testing where either general relativity can break down or where the standard model can break down. And it's either, well, it's both frustrating and again also humbling still that at the moment we have not seen any significant deviations from the predictions of these two theories. The only strong evidence that the standard model is in itself not complete is given by a couple of measurements. One is that neutrinos, which are a peculiar type of elementary particles, that they have a mass. The mass is small, but they nevertheless have a mass. It's an aspect which is not incorporated in the standard model itself. It can be easily bolted on, but it makes the standard model less elegant. It makes it more contrived. That's one aspect. And then the other aspect is, for example, also the reason why we have an abundance of matter over antimatter in the universe that relates to another fundamental symmetry of the standard model, which is so-called CP symmetry. And at the moment, we would need to incorporate new physics in the standard model in order to make the deviation of this CP symmetry so strong that it can explain why we have a universe which is dominated by matter and not by antimatter.
Do you believe that by studying, by better understanding black holes, we might better be able to understand the Big Bang, our origin, and thus consequently sort of back engineering, trying to resolve all these problems that we have from the Big Bang time?
Yes, I think studying black holes Well, there are many connections also between the study of black holes and particle physics, because in a way, black holes, although they are exotic objects, they are extremely simple to describe. They can be described basically by three quantities: their mass, their spin, let's say the speed at which they turn around their own axis, and their electric charge, and that's it. And so it's basically the same kind of properties that also characterize elementary particles. So in terms of theoretical description, a black hole can be described by the same elementary quantum numbers, if you want, as an elementary particle. And although I'm not a theoretical physicist, there are many avenues in theoretical physics that try to make connections or translations between these two domains, between these two frameworks of physics. The question is now, will they finally produce testable predictions that can be tested either by experiments on Earth or by by doing cosmological or astrophysical observations? At the moment, they are not yet there, but I'm confident that in the near future, in a couple of decades from now, we will get some predictions that can actually be tested, also with experimental apparatus that will be sensitive enough to detect these deviations.
Okay. Do you also think that we will ever, okay, let's say that the standard model has many elements, particles, force, carriers, and all of these elements, they have specific numbers as mass, correct me if I'm wrong, as mass, charge, and spin.
Mm-hmm.
And do you believe that the standard model, or whichever theory will it be for the standard model, will be incorporated into it the reason why, or at least it will emerge the reason why the numbers of the elements of this theory are the numbers that we measured, sort of as a reason why these numbers are the numbers they are, or the explanation will simply be, oh, well, they are like that simply because they work for life,
Yeah.
and we are life, and we see them.
So the standard model in its current form is extremely predictive. It can predict the outcomes of thousands of different measurements and experiments. Okay, but at its base, and it as I said, it is so elegant that it starts only from a very limited amount of assumptions of abstract symmetries of time and space. Now, this in itself is a remarkable, really a remarkable feature that is difficult to appreciate by a person who has not studied the mathematics of the standard model, but it's truly beautiful. Now, the standard model does not predict everything. So depending on how you look at it, the standard model has roughly 15 free parameters. It means there are quantities that the standard model in itself does not predict. They need to be measured from experiments. And once you have measured them, you can use them to make this huge plethora of predictions that the standard model can make. But roughly 15 parameters are parameters that you need to measure by experiments. They are typically the masses of the fundamental particles. They are encoded in a so-called coupling constant, which relates how the Higgs field couples to these particles. And other particles, other parameters are the so-called mixing parameters of how quarks and possibly also leptons intermix with one another in the standard model. And I can tell you that these parameters have been very accurately measured, but it is basically also through the process of measuring them extremely precise that we can do consistency tests between if you measure parameters with one series of experiments, they can also again have an impact on the outcome of other experiments. And so what we try to do is to see if there are tensions between the outcomes of these experiments. If the outcome of one experiment through the prediction of the measurement of parameters in another one do not match anymore, it means that there are new elements in the standard that need to be added to the standard model that we need to study, that we need to extend the standard model. And so this is the aim of the game of modern particle physics, to constantly do consistency checks whether everything we measure in the standard model, including the measurements of its fundamental parameters, are consistent with all the predictions it can make.
Okay. It remains to the question of why these numbers are
Why?
the
Yeah,
way
yeah.
they are.
Okay, that finally boils down to almost a philosophical question, right? Yes. Why do the constants of nature have values that they currently have? Because, as some people claim, otherwise, the conditions to create life would not have been there, and there would be no human beings to pose the questions in the first place. Other speculative, it's a bit to me a bit of an easy. This is the so-called anthropic principle, right? To me, it's a bit of a sneaky way to escape the question.
I completely agree.
It is what it is because it was what it was, or something like that. But okay. Yeah, it basically we should simply say we are ignorant to the reasons why these parameters are what they are. Other solutions can be that there can be multiple universes or even regions in our universe where these parameters could have different values. And the physics, what we know for sure is that then the physics in these regions of the universe or in these universes would be totally different than the physics we see here in our current, in the universe we live in. So other people can say it's an irrelevant question to even speculate about what might be happening in other universes, which we are never able to observe, from which we are completely causally disconnected, etc., etc.
Okay.
But it's true that there are a couple of parameters that are, well, it's called in particle physics, the fine-tuning problem. Certain parameters need to be so precise. You could say, okay, the parameter is this value, plus or minus this value. You can multiply it with a factor 2, it's still okay. You can divide it by a factor 2, it's still okay. But some numbers need to be exactly that value up to 10 decimals. And then you can think, why on earth would the universe be so delicate that this needs to be this value up to 10 decimals? If you would change a little bit, the whole physics would be completely different. These are the so-called fine-tuning problems. And again, there are extensions of the standard model that give a natural explanation why the values are what they are. Things, theories like supersymmetry, for example. But by doing that, you again create another set of parameters, which value you then have to explain again from scratch. So it's a bit of a never-ending story. And it might be related to the fact that in formal mathematical logic, there is never a theory which is able to, let's say, explain that is mathematically and logically consistent with itself.
Which is the Gödel incompleteness theorem,
Yeah,
right?
right.
Now, regarding the fine-tuning, I wanted to ask you, you are a man of science, right? You have been studying and teaching these subjects and these topics for a long time. Do you believe in the fine-tuning as in there being something greater than us that we cannot understand through science and that we just have to accept that we cannot understand? Or do you believe that all of these fine-tuning included is truly and purely random?
Yeah. Okay. That's a question with different facets, right? You're basically asking me, on the one hand, whether I have philosophical convictions that go beyond pure materialism and pure empirical science. On the other hand, what do you mean with belief? What I believe as a scientist, I believe in I believe in the empirical method, which means that each hypothesis you pose about the universe, about nature, should be empirically verified and testable. And so conjectures that are currently not experimentally testable in any way, either directly or indirectly, are basically have little scientific value. They can be perhaps nice philosophical or mathematical exercises, but they are not. They have little physical value. It is only when theories are experimentally falsified that you can say, I believe in this theory. And then you believe in the theory until there is at least one experiment that contradicts the theory. And then your belief in the theory should slowly fade away, and it should be replaced by a better version of the theory. This is how the whole evolution of science works. Or, as in some cases has also happened, you could also not believe in the outcome of the experiment, and then you need to develop new experiments that are complementary or that are copies of the experiment to check whether the measurement is indeed properly done or not. So in fact, to me, this is a form of believing that has nothing to do with faith or religion. Faith or religion is another thing. If you have faith in something, it means that you accept a statement, and at the same accepting that you will never be able to find a physical or mathematical proof that this is true. So faith, in that sense, is accepting something for which you don't have proof. And that's, to me, the domain of spirituality and religion. And that's a personal aspect that every human being needs to find a balance between. There are people that are extremely materialistic, that say we are basically a large bag of chemicals. We are born for no reason, and we die by simple oxidation process, because that is what's actually happening when our cells age, they oxidize. So we basically die from rust at the cellular level, right? We have no purpose in life, and there is no specific role in the universe for us humans. We are probably not unique, and therefore, we have no special role to play in the universe. I've been for a very long time struggling personally with this idea. And to some point, I find it very unsatisfactory to live with the idea that we are simply a bag of chemicals without any purpose or intent in life, that all our actions are basically meaningless. So I tend to, let's say, I have developed a little bit of a more spiritual side that allows for allows me to stay open for the doubt that we will never know if there is a sum that exceeds that there is an entity or something that that exceeds the sum of all the parts. We will not know for sure whether there is something beyond death, and we should therefore strive to live a life that has at least some meaning for us and for the people we care about. And when discussing with people that, especially also from cultures that have a very rich spiritual culture, like, for example, the Indian culture, people in India. When I asked Indian colleagues, how can you believe in the exact laws of physics and at the same time believe that there are some demigods or partly animal-like, etc., etc.? And these people say, and that's what most spiritual scientists say, is that these are basically two parallel tracks of reasoning. One is in the rational, material side. The other one is in your spiritual part of your life, of your being. And these two tracks, they can develop in parallel. They don't necessarily need to meet, or they don't need to be necessarily reconciled. What you consider as useful, rightful, meaningful in life does not necessarily need to be connected with material or empirical aspects of the physical reality of the universe. What I do object against is that in modern cultures, well, also in ancient cultures, that often metaphorical concepts about spirituality are intermixed with physical realities, and that also, for example, archaeological history is confused with spiritual history or biblical history. And these kind of things are dangerous for people that are less critical to see the distinction between a symbolic language and a scientific exact language.
Okay.
Does that make sense to you?
Yeah, absolutely. I had a question. You just said that relating to your Indian colleagues, that they see indeed that these two worlds as parallel tracks, that they do not intersect each other and they do not interact with each other. On one side you have the rational, the material, and on the other side you have the sort of irrational, the spiritual. Do you think that a possible bridge between these two tracks could ever be achieved by what could be called in the future, probably, a theory of consciousness?
It's a question I cannot answer. I cannot say yes or no. I don't know. But I think part of life and part of becoming a little bit wiser in life is probably also to accept that certain questions don't have answers.
Lagrange would be sort of an advocate of saying, I do not know, indeed.
Mm. I know one
Okay.
thing for sure, and that is I do not know. But I think we should also, I mean, we are somehow obsessed as modern human beings to know things for sure. And I think parts of the richness and the adventure of life is uncertainty and embracing uncertainty. And learning to live with your doubt is probably one of the, let's say, first sign of developing some form of wisdom in life, accepting and learning to live with doubts.
Have you been more when you were younger? Probably were you more prone to expecting and wanting to know everything, to know the truth of
Yes,
everything?
yes, absolutely. I thought that everything had an explanation and everything needed to have an explanation. I think as you get older, you tend to accept that not everything needs an explanation. Often let's say the mystery or the openness or the doubt makes it more beautiful or makes it more attractive than having an explanation for everything.
Okay, regarding explanation, I want to ask you whether we have an explanation for gravitational waves within the standard model.
No, the standard model in itself does not predict gravitational waves because it does not incorporate gravity as an interaction. What is remarkable is that almost immediately after he published general relativity, Einstein himself predicted the existence of gravitational waves. That, in fact, one of the simplest solutions of Einstein's complicated equations, called the Einstein field equations. And that the other remarkable fact is that it took then 100 years after that prediction for people to finally detect these gravitational waves. And it's also remarkable that some of the most brilliant scientists of our times have dedicated at least 50 or 60 years of their life to build experiments that basically gave no result. They didn't measure it, that they had the stamina and the persistence to continue to work on these experiments until then they were finally rewarded with the discovery of gravitational waves. And by the way, is a fun fact. If you connect the scientists that were key to the measurements of the cosmic microwave background and the scientists that were key to the construction of the first gravitational wave interferometers and that finally measured the gravitational waves, there is a large overlap between these people. For example, Ray Weiss, the person who got the Nobel Prize in 2017 for the discovery of gravitational wave, but coming up with the concept of the LIGO laser interferometers, was also one of the scientists that was the proponent of the Kobe satellite mission, which was the first satellite that fully measured the full spectrum and the first map of the fluctuations of the temperature in the cosmic microwave background. So you see that this person could have, if he would have been a bit older, perhaps a bit more senior as a scientist, he could have already gotten the Nobel Prize for the results of the Kobe satellite, which were given to two of his more senior colleagues at the time. And that's what you see with a lot of brilliant scientists, is that they could have gotten the Nobel Prize 2, 3, 4 times in some cases. There are a few scientists that got the Nobel twice, a limited amount. You know which ones in physics?
I know of Marie Curie.
Marie Curie got it twice, and also John Bardeen got it twice. Once for
Right.
the discovery of the diode, the semiconductor device that is now at the basis of modern microchip technology, and then secondly for his theory on superconductivity that describes how superconductors work. So it's actually even more remarkable because it's a guy that got the Nobel Prize both for an experimental discovery and for a theoretical discovery.
Okay, Einstein only won, however.
Einstein only won, but he could for what? Do you know what Einstein got the Nobel Prize for?
The photoelectric effect, which
Yeah, right.
said like that is not really exciting.
Well, yeah,
As
it's
a
one of
name, is not exciting. I know that
no.
I just heard. I was just listening to a podcast with Sean Carroll, and he says, "Yeah, the name is really not exciting, but the problem is that in that paper he posited the existence of the photon." So,
Yes, yes. Yeah, so, but it's remarkable that he could have gotten the Nobel Prize for his theory of special relativity. He could have gotten the Nobel Prize for
general
the
relativity as
general
well.
relativity. And he also predicted the stimulated emission of light, which is at the fundamental principle that explains the working of lasers. So he could have got 4 Nobel Prizes.
Why didn't? Why didn't he though?
I don't know. I think when I read more and more about Einstein, is that he was a character that was often very insecure about his own predictions and theories. He often made a statement, then retracted the statement again, then put again out the statement, then retracted it again. So he was a guy that was often in doubt with his own ideas or in conflict with his own ideas. If he would have been a bit more, let's say, self-secured about this, but I assume he was a self-confident person. But in terms of his work, I think he's given too much the signals of I'm publishing something, but I don't actually believe what I'm publishing here.
Yeah, that is true also for black holes. He didn't believe black holes could exist for I think for all his life.
Yeah,
Or did
also,
he got
also
convinced at some
Yeah,
point?
also other aspects like the cosmological constant is one of these on-off stories. Also the fact that, for example, for gravitational waves, that gravitational waves were a real physical phenomena, that they would travel with the speed of light, that they would carry energy. This was a thing which was continuously perturbed about. He didn't really know what it was.
And how do you in principle notice that a gravitational wave has passed? Because if I'm being asked how do you know there is electromagnetic radiation, well, let's be a bit more specific. How do you notice there is electromagnetic radiation in the form of visible light? Then I'm telling you, well, it's just because I saw the light. How do you notice in
But
principle?
did you see the question is what do you mean? But I saw the light. If it's visible light, you can pick it up with your own eyes.
Yeah,
But
exactly.
we are looking with telescopes in the infrared up to the ultra high violet, X-ray, and gamma ray spectrum. You cannot see these things with your eyes. So you have to rely on some meter or some interpretation of some instrument which tells you I'm seeing something here, right?
And how do you notice
So,
for example, when a gravitational wave has passed? How does that work in principle?
yeah. So in principle, so gravitational waves are what are often called the robot perspective solutions of Einstein's general field equations, which means that if you sit in a rowing boat, a small tiny boat on the ocean, first of all, the ocean around you is approximately flat, and the waves surrounding you, every 10 meters, there is a kind of a crest of a wave surrounding you. The waves can be characterized simply by either the angle of the water you see when you look at the horizon, or the amplitude, the height of the wave in regards to that flat surface. Both can be considered as tiny perturbations on the overall scale of the flat ocean in which you are working. If you apply the same philosophy or the same idea to the metric of completely flat space-time, it's called the so-called Minkowski metric, and you perturb this flat space-time with a tiny perturbation, you fill it in the Einstein field equations without any further assumptions, you get the equation of a wave, just like a wave on the ocean or a wave of electromagnetic light. This is the same. Basically, a sine or a cosine with an amplitude, with a frequency, and if needed, a phase. And so these solutions are extremely simple. Now, the basic key, the big calculating challenge lies in what are the sources of these gravitational waves. And for that, you need to compute, make quite complicated numerical calculations of Einstein's field equations, assuming some form of energy distribution of your system and how this energy distribution evolves in time. But gravitational waves itself is a solution of Einstein equations that can be basically calculated and understood by a second or third year student in physics, right? And they have extremely simple form. Now the question is, what does such a wave do? How can it be detected? So what it does is it periodically, or in a time periodically, let's call it more generally, in a time varying way, it can stretch and expand space as it travels throughout the universe. So when it finally arrives here on Earth, every ruler and also every clock you would have here on the planet would temporarily be affected, either stretched out or compressed via a specific time pattern by this gravitational wave. Now, it appears that the most accurate measuring rulers and the most accurate clocks we can build on Earth are lasers. And so rather than just taking a ruler and seeing how much this ruler would change, what you do is you shoot laser light in two perpendicular directions, split halfway by a half transparent mirror. You shoot one laser beam in one direction, the other one perpendicular to it. This laser light can bounce several hundreds of times back and forth between nearly perfect mirrors, perfectly reflective mirrors that are also perfectly suspended as if they were in free fall. Now, if a gravitational wave passes through the Earth, one arm of this experiment would temporarily contract, while the other one would temporarily expand a little bit, which means that the time the light needs to travel back and forth between these mirrors differs between these two arms. In one, it will take less time. In the other one, it will take more time. Now, this introduces in optics what is so-called a phase difference. If you have the waves of the one light and they are not arriving at the same time as the other, they're kind of shifted with respect to each other. If you add these two waves, if you combine these two waves, then they result in either more or less light than the original laser beam. And so what you measure at the output of this interferometer is a change in light intensity after the recombination of these two paths of laser beams that have taken a little bit less or a little bit more time to travel in one of their arms. And the big technological problem is that, first of all, everything, the effect you want to move is of the order of a factor 10 to the minus 21 or 10 to the minus 24 relative change in length of these arms and also in travel time, while the wavelength of this light is of the order of a micron, so 10 to the minus 6 meters. So you have to measure an effect that is 15 orders of magnitude smaller than the actual wavelength of the light you use. And also everything in the experiment is basically vibrating with amplitudes of also a micrometer over a quite broad frequency band in which you want to measure. So everything is shaking over distances of 10 minus 6 meters, The light itself has a wavelength, a basic unit of measurements of 10 to minus 6 meters. And the effect you want to measure are relative changes in length of these laser arms of the order of 10 to the minus 21. Or if you have a length of the arm of, let's say, of the current experiments, a few kilometers, it means that you're measuring absolute changes in length of the order of the diameter of a proton, less than the diameter of a proton. And the only way to do this is by all kind of clever technological tricks. And it is this is the reason why the principle of this measurement is so simple, and people knew how to predict the size of the effect that gravitational waves would have. But it took 40, 50 years to make the technological advancement that would control all the noise sources and would make the experiment so sensitive that it could detect this tiny effect. It's through persistence that we have finally succeeded in measuring it, which is to be, again, a remarkable achievement.
How, sort of the setup of the experiment, how would you rate it, let's say, on a scale of cleverness? Meaning, is it intuitively a very clever way of measuring this effect of gravitational wave, or after all, it is a rather straightforward and intuitive?
From first principles, it's a concept which dates already from the 19th century. It's an experiment done by Michelson and Morley, which evolves, well, they basically wanted to test another hypothesis, the existence of a substance called the ether, because at the time they believed that light, electromagnetic waves, needed a medium to propagate. They did not understand yet that light is basically a system of electric and magnetic fields that sustain each other in a quite interesting way. And therefore, light does not need a medium to propagate. It can propagate in empty space or vacuum. At the time, they thought that just like sound wave or pressure waves, that light needed a medium to move into. And that was called the ether. That's why I think, at least in my language, when a radio station or a TV station starts to broadcast, they still say, we are on the ether. Do they also say this in Italian?
I don't think they do.
Okay.
Or maybe I've not heard
At
of
least
this.
in our language, they still claim that, okay, we are now recording, we are now transmitting the radio thing, we are in the ether. It's still a language used. So, but at the time, they tried to prove the existence of this ether, which means that if the ether would be a substance permeating the whole universe, our planet would move through this ether. So this would mean that in the direction of motion of our planet, then we would shoot light back and forth between two mirrors. That you would have to add the velocity of our planet that would move through this ether, while in a direction perpendicular to it, there would be no effect of the velocity of the Earth on this velocity of light in the ether, right? And so they measured, of course, no difference in velocity of light between these two arms, which disproved the existence of the ether. But this whole concept of this Michelson-Morley experiment lies at the basics of gravitational wave interferometry. However, the sensitivity of this naive Michelson and Morley experiment would be of the order of 10 orders of magnitude worse than the actual sensitivity you need to achieve with current instruments. And so the cleverness is in all the tricks you need to do to increase the sensitivity of the experiment. And these tricks, they go pretty far. They go up to the level of quantum optics, material science, etc., etc. And then some other tricks are basic, almost basic textbook physics, but I find them nevertheless extremely nifty or extremely clever, because they are they are simple mechanical tricks that allow you to suppress, for example, the shaking. The seismic noise of the mirrors is basically suppressed by hanging the mirrors on a long series of coupled pendula. And the analogy that is often explained by the guys who designed it is that if you have a yo-yo, for example, hanging on a string, and you move the suspension point, the top of the rope that holds the yo-yo, very quickly you see that the yo-yo on the bottom, the mass doesn't move much. So at high frequency vibrations, this motion of this mass hanging on this pendulum is actually damped, and is damped quite strongly. And the more pendulum you connect to each other, the stronger this is damped. So this is a way to reduce the amount of seismic vibration at high frequencies by 14 orders of magnitude, for example. However, at the low frequency, if I walk around with this yo-yo will simply follow my motion. So at low movements, low oscillation frequencies, this damping doesn't work at that level. So luckily, you can then control it by other means. You can measure the seismic fields and you can couple back to a electrical system that can steer the mirrors. Like it's done in a way like a marionetta, like the way a puppet player controls the movement of a puppet. But still, the physical principle that a system of coupled pendula can suppress vibrations at high frequency is again basic classical textbook physics. Nevertheless, to use it in a modern day experiment, I think is extremely cool.
So probably, sorry.
No, go ahead.
So basically, the experiment is more, let's say, we can classify it more as a engineering prodigy other than an intellectual prodigy, the detection of gravitational waves.
Well, I would say both. It's one of these prime examples of research infrastructure. And I can say that these large research infrastructures, such as large astrophysical observatories, gravitational wave experiments, particle accelerators, they are, let's say, the cathedrals of instrumental science, right? They are the Stonehenges of the of the 21st century, right? And they require such a combination of expertise, both at the level of various disciplines, at the level of material science, optics, mechanics, computer science, microelectronics. So they need to bring out the best of all these disciplines at the fundamental level in order to come up with the concepts that you need to achieve the sensitivity. But then on the other hand, it needs to be implemented in practice. You can think of a very nifty mechanical device or an optical device, but if you cannot build it according to the specs that you require, it's also pretty useless. So it's both at the level of conceptual thinking, where you need to, again, connect many dots, many areas of different areas of science, then at the level of actual implementation, and at the actual level of fabrication and exploitation of these things. So it's really a combination of both physical and engineering ingenuity on paper up to, let's say, guys or girls that are actually capable of keeping control of a complex system that consists of so many knobs to turn. And the challenge in an optical system like a gravitational wave interferometer is that you cannot simply optimize one parameter of your system by turning one knob, then optimizing the other knob. Everything is coupled with everything. It's like tuning your guitar, but you cannot tune each of the strings individually. If you start to tune one string, the other 5 strings go out of tune. So you actually have to tune all these 6 knobs at the same time. So the difference is that these experiments do not have 6 knobs, but 6,000 knobs, right? So to understand the engineering complexity and the operational complexity of these instruments.
Okay. What do we learn from gravitational waves? Because of course we do know very precisely the properties that we learn about objects through electromagnetic waves, but what do we actually learn from these gravitational waves?
I think we can learn many things, but I think the biggest puzzle we try to solve with studying gravitational waves is the fact that we now know that in most galaxies, at the center of the galaxy is a supermassive black hole, which is the whole engine, the dynamo that keeps the galaxy together, and it can have masses of several billion times the mass of our sun. Now we know that in order for such an object to form, it must be extremely exotic. So they are assumed to be black holes. And in fact, recently, since 2019, we can take pictures of these supermassive black holes. This is the results of the so-called Event Horizon Telescope collaboration. So we're now taking pictures, actual photographs of centers of galaxies that prove that A, there is a massive object with billions times the mass of the sun, and it is a black hole. It has all the properties of a black hole, right? Now we know that black holes need to be formed in principle from stellar collapse. When a star dies and is heavy enough, and it's only roughly 1 to 3% of the stars that end up as a black hole, that the star collapses and that what is left of the core can turn into a black hole. So black holes, when they are created, they typically have masses of the order of 2, 3, up to maybe 20 times the mass of our sun. Now, the big question is, how can, if that's the primary way to form black holes, how can you create monsters that are also black holes of billion times of the mass of the sun? Then they say, okay, when two black holes meet, they can dance around each other for a couple of 100 billion years, and then they can merge to form a heavier object. But if you count the amount of successive mergers you need to do in order to create from, let's say, black holes of the mass of 10 times the mass of our sun, an object with a few billion times the mass of our sun, the time you need is much longer than the age of the universe. So either we do not understand how supermassive black holes form, or there must be mechanisms that speeds up this formation process. Or there must be ways that there existed already black holes before the first stars were created due to density fluctuations, topological defects in the structure of the universe that would allow very tiny small black holes to be formed before even the first stars were formed, that were then the seeds of what are now these supermassive black holes. So I think gravitational wave astronomy tries to solve the puzzle of how, either in a random or in a dynamic way, black holes can successively merge to make heavier and heavier and heavier and heavier black holes. That's one of the main puzzles. It tries to do tests of general relativity. It tries to measure the speed of propagation of gravitational waves, for example. It can provide an independent measurement of the Hubble constant, which provides, again, an independent way of measuring the age of the universe. It can provide indirect information, again, on the energy content of the universe and the way it evolved, right? And then what it can also do is it can study exotic astrophysical objects. Besides black holes, we also know that there are neutron stars. A neutron star is a star that was basically not massive enough to form a black hole, but the gravitational attraction of the matter in the neutron star finally allowed that electrons were pushed inside the protons to create neutrons. That's why a large part of this star consists of exotic matter consisting only of neutrons. We are not able to create this type of matter in any laboratory. So studying this neutron star can reveal something on the interactions of how this neutron matter, or maybe even more exotic matter, interacts with each other. And one of the probes is that if a neutron star and a black hole revolve around each other, the black hole can deform the neutron star. It can cause tidal effects like the moon has also on our planet, right? So it can cause small deformations on one side of the neutron star. Currently, the limits we have posed on these deformations are so strong that we believe that the neutron stars are the most perfect spherically symmetric objects in our universe. So future measurements will indicate whether we can detect such deformations and whether we can derive the so-called equations of state, or derive the strength of interaction between the constituents of exotic objects such as neutron stars. And then the ultimate goal also in terms of cosmology is, of course, to measure also the existence of the equivalent of the cosmic wave background, but in gravitational waves. And the reason why this is so interesting is that I told you in the beginning of our discussion that the cosmic microwave background provides a time in the history of the universe through which we cannot gain any information anymore because the universe was not transparent for its own light. Photons only decoupled when the universe was 380,000 years old, when it had a temperature of 3,000 degrees. Gravitational waves, probably have decoupled already during the epoch of inflation. So if we would detect specific structures in a map of the energy fluctuations in the gravitational wave spectrum, we could deduce effects that relates to physics happening in or just after the area of the time era of inflation, which is 10 to the minus 30 seconds after the Big Bang, that order of magnitude in time. So the amount of gain of information we have in terms of time, let's say, the time we can approach after the Big Bang with gravitational wave is almost unlimited.
Now, I would like to ask you about the Einstein Telescope, because we are talking about gravitational wave detectors, and we are now building in Europe the so-called indeed Einstein Telescope. How is it different from the previous gravitational wave detectors, as LIGO, as you mentioned before, and Virgo? What are sort of the objectives that it has? And I would also want to ask you, um, you just said that we could probe through gravitational waves. We can theoretically, in principle, probe up until 10 to the minus 32nd after the Big Bang. What is something that you would not expect to find at 10 to the minus 32nd after the Big Bang?
Well, I think it's more sensible to say what kind of stuff can you expect to happen there. You can expect that well, you would need you would see effects that correspond to matter and energy fields that go way beyond the standard model. The standard model should break down at those energy scales and at those time scales. What these are, well, there's huge amounts of possible variations and models and theories that describe what could happen there, ranging from extra particle fields to a specific effects called the phase transitions in the universe, specific objects called cosmic strings that are topological defects in the fabric of space-time, etc., etc. So there is a huge scala of models and predictions of what could have happened there. And if we were able to measure the signals coming from gravitational waves in the early universe at that early stage, we will be able to distinguish, to rule out certain scenarios and to find more hints that other scenarios are more plausible. At the moment, they're all speculative. So no way to tell which one corresponds to physical reality. To come back to your other question, what was it again? What the Einstein Telescope, what will it change with respect to the current instruments? First of all, I have to correct you. The Einstein Telescope is currently not being constructed. Its construction is being prepared. And so we will finally decide in 2026 where the Einstein Telescope could possibly be built. There are currently two candidate regions, one in Italy, in Sardinia, and the other one in the border region between Belgium, Germany, and the Netherlands. And around 2026, it will be decided what would be the preferred location of this experiment, of this new instrument. And then the construction could start most likely a couple of years after this decision, because then the detailed engineering studies need to be done for the actual civil construction. Civil construction would take roughly 5 years, so the thing could then be operational by the year, let's say 2032, 2035. That's the idea. I must say also there is an equivalent project in the United States called Cosmic Explorer that basically aims to achieve the same sensitivity. So what kind of sensitivity do we want to reach? First, if the current laser interferometers in the US and in Europe would reach their design sensitivity, they will measure something of the order of a couple of hundred of mergers, maybe up to 1,000 mergers of binary compact objects per year. So two black holes or two neutron stars or a black hole and a neutron star. That's good because we currently measure now something of the order of 1 per week. Okay. So although this is very interesting, we know that these populations of all these black hole and neutron stars that are merging are extending far beyond our current observational horizon with the current gravitational wave telescopes. In terms of a quantity called redshift, we can look only now up to redshifts of the order between 1 and 2, which is relatively close in our cosmic neighborhood. Now, the fact is then that these populations are sitting much further away, or they extend much further than that. And we also believe that these populations should increase with distance up to a certain distance. And then it falls off rapidly because then you arrive at the distances or the moments in time when no stars were actually created and where therefore also no black holes could exist, provided that all black holes are produced at the end of the life of certain specific stars. Okay. So what do we want to do? We want to extend the overall sensitivity of these gravitational wave instruments with another factor of 10. So we want to make them capable to observe signals that are 10 times weaker than the current signals we are able to detect. And by doing so, we effectively can look in terms of distance 10 times further in the universe to see the same objects as we see now, but as if they were standing 10 times further away from us. If you do that, it means also that you increase the volume of the universe you can observe, not by a factor 10, but by a factor of 1,000. And so this will drastically increase the amount of observations you can make of gravitational wave events. So while we are currently seeing now roughly 1 gravitational wave detection per week, you would see in those conditions thousands of gravitational wave events per day. So of the order of millions per year. Okay. And this allows you, of course, to do much, to evolve from a time period or an era of discovery science, where you basically start to see the first individual signals and start to make sense of it. How does it fit with general relativity, et cetera, on an observation by observation base, to an area of precision science where you can make predictions and statements about the whole populations, about the tails of these populations, and can do much more precise measurements because you're building up statistics. Okay. And it also implies that you will be able to see these rare or exotic objects in the universe, which should also emit gravitational waves, for which at the moment we have no experimental evidence yet. There are other gravitational wave signals that are more difficult to detect because they are not so big in amplitude, or because they are shorter in time, or because they are, let's say, more difficult to predict what the actual waveform is that you're trying to see there. So with these future experiments, we will be able to see also these things. And that's why we want to increase the sensitivity with a factor 10. Another aspect of the current experiments is the bandwidth or the range in frequency of gravitational waves that you can observe. Typically, we observe now, we are sensitive in a frequency band between 10 Hertz and a couple of hundreds of kilohertzes. And this limits the mass of the black holes that you can observe. The heavier these black holes are, the lower the frequencies of gravitational waves they typically emit. So that's why, for example, other experiments that are going to be conducted in space by satellites will be more sensitive in this very low frequency band, and they are therefore more sensitive to picking up signals from extremely massive black hole mergers. Now, another thing we want to do is that if your bandwidth is so limited, only in the last fraction of a second, when black holes are spiraling around each other to finally form a new black hole, for example, only in the last, they've been doing that for tens of millions of years. And only in the last fraction of a second, in the last half a second, we see that the signal enters our bandwidth of the experiment. So we only observe the last half a second of the lifetime of this object. What we can do is that in certain cases, when it is a merger of two neutron stars, for example, when we observe this in the last couple of minutes of its life, we send out alerts to all kind of other observatories in the world, satellite-based, ground-based, to go and look at the patch in the sky where we receive this gravitational wave signal. The reason why we receive the gravitational wave signal before any optical or radio signal is that the system already emits gravitational waves when it's still rotating around each other. Only when it merges and it produces a big explosion in the universe, then you can see optical and other kind of signals. And so, if you make the bandwidth of your instrument larger, you can see it earlier and you can observe it longer. So you can also send out these alerts much earlier in time, and allow all kind of observatories to prepare well in advance to go and observe this merger of these two objects, typically two neutron stars or a neutron star and a black hole, over the whole range of the electromagnetic spectrum, ranging from radio waves to infrared to visible light, UV, X-rays, gamma rays, and even neutrino detectors can look at these things. And this is a form of astronomy which is called multi-messenger astronomy. So in order to make this multi-messenger astronomy more effective and accessible, we need to extend the bandwidth of these gravitational wave detectors. So ET and Cosmic Explorer will make the overall sensitivity of the measurements better to look further in the universe, and it will also increase the bandwidth roughly with the same amount. It will increase the bandwidth with a factor 3 to 5 if you wish. But this has a tremendous impact on the amount of physics you can observe with it. And the way it will be done is, in fact, the choices between the US project and the Einstein Telescope are different. What the US will do is they will basically scale up LIGO to have basically longer arms. LIGO now has 2 interferometers separated by a distance of roughly 3,000 kilometers, and they each have perpendicular arms with a length of 3 to 4 kilometers. What they want to do is create again 2 Ls separated by roughly that distance, but with arms of 40 kilometers. If you make the length of the arms longer and you make also the power of the laser light much longer, you're making the experiment more sensitive to smaller signals. Here in Europe, it's very difficult to make an instrument with arms of 40 kilometers. So that's why we've chosen for a more compact solution, which is an interferometer with arms of 10 kilometers. But we decided to do 2 things also because we don't want to spread these things over our territory over 3,000 kilometers. We decided to make them all in one location. And in order to pinpoint a location in the sky where you can then point to other astronomers saying, look, there was a gravitational wave happening at that patch in the sky, you need at least 3 interferometers. So that's why we thought of the shape that would combine 3 interferometers in the most compact way, and that's by making an equilateral triangle, where in each of the corners of the triangle you have an interferometer. The angle between the arms is then not 90 degrees anymore, it's 60 degrees, but it still works. It's a compromise you need to do. And then secondly, the reason why the sensitivity of these measurements are dominated are different in the low frequency range and in the high frequency range. In the high frequency range, you're essentially dominated by the amount of optical power you can put in the system. The more light you can pump in the system, the more clear your measurement and the more sensitive your measurement will become. But at the low frequency range, the more optical power you pump into the system, the more you're going to move the mirrors by the actual pressure of the photons against the surface of these mirrors. So it's a kind of problem that you cannot solve at the same time. So that's why we decided to decouple the instrument in fact, two instruments, one that will operate at very high optical power, that will be sensitive for the gravitational wave frequencies at high frequencies, above a few hundred hertz, and then an instrument that will typically operate at low optical power, and for which the mirrors will also be cooled to temperatures near the absolute zero, roughly 10 Kelvin, in order to make the measurements at the very low frequencies as precise as possible. So the Einstein Telescope is actually a complex of 6 interferometers, 3 in each corner, 3 corresponding to the 3 corners of the equilateral triangle. And in each interferometer, there will be, in fact, 2 laser systems, one cold one and one room temperature version that will operate simultaneously to optimize the whole sensitivity over this whole bandwidth. And this makes technologically the Einstein Telescope project technologically more challenging than the American project. Americans solved the issue by simply scaling up, and we solved the issue by basically combining a couple of specific techniques in one instrument. So we'll see which one performs the best in the end. It's clear that, and I hope that both the American project and the European project will be realized before I retire. And then we will have, again, a global network of several interferometers that can operate in conjunction with each other, like is happening now with the 2 LIGO detectors in the US and the Virgo detector in Italy and Europe.
Wow, listening to this makes me so excited about the future of this indeed observation, but at the same time it makes me sort of puzzled in a positive way, because I think I was hearing this reasoning from Brian Cox, where he said it is popular reasoning, it is popular telling that we human beings are simply stardust, so we are a product of the dust that stars have been expelled. So at the end of the day, we are no external object in the universe. We are simply part of the universe itself. And the fact that we could, through our through our complexity, we could get to understand the working of the universe itself is as if a part of the universe itself is discovering itself. And this is very, I would say, not intuitive, probably, because we give it for granted, because it is the way it has always been, and it will always be as long as we will be around. But if you think about it, it is not meant to be the case. And so I find it extremely fascinating, exactly as sort of an internal discoverer of our homeland, which is our universe. And I would like to ask you, mentioning a quote from Stephen Hawking in the book A Brief History of Time. I would like to ask you sort of a question. And the quote basically goes like this, and it says, even if there is only one possible unified theory, it is just a set of rules and equations. What is that breathes fire into the equations and makes a universe for them to describe?
Yeah, I agree with that statement. I think it's always dangerous to assume that what we are discovering in terms of the physical laws is an absolute truth, and that these laws are absolute. I think what we're merely doing is providing an extremely nice description of what we see. We try to explain the complexity of our surroundings and also the beautiful patterns we see in that complexity by a set of rules. But to me, it simply remains a description, a very weak attempt to describe in probably extremely naive terms and concepts of what's going on in nature. Nature doesn't need rules or laws to function the way it functions, right? So we are not masters we are not telling the nature how it should behave. nature is telling us, well, nature is revealing to us more or less what it does. And with our limited senses and our limited vocabulary and our limited philosophical concepts, we're trying to make sense of what nature does. And we describe it in a rather primitive and naive way, I think. And I think I have another affinity, for example, with art. And I think what distinguishes art from science is that art can often provide a way of expression via images, via text, or via music, for which we have no words yet to express what we mean. So I think often art tries to is ahead of the scientific method in the sense that it tries to express things for which we have not yet formulated concepts in our mind, let alone a vocabulary, let alone a mathematical description of what we are talking about. And I think that makes it very enriching. And I think that also means that artistic people and scientific people should discuss more often and should try to understand each other more often. And whatever happens, I don't think that we are formulating a kind of absolute truth or an absolute law of nature. We're simply describing in a very primitive way what we see. I would say if archaeologists in a couple of millennia from now will dig up our remnants, our civilization will have probably been destroyed or extinct. If history repeats itself, our culture will extinct, will go extinct, or will be replaced by another culture if we are lucky. And when archaeologists from that culture will find our old documents and manuscripts, which is also again a bit funny because will we still leave behind some kind of retrievable documents? Or will everything be disappearing in the electronic, primitive electronic noise that we are essentially generating the last decades? But still, if they find the information of what we were thinking and doing, and also if they dig up the installation like accelerators and laser interferometers we have constructed below ground, they will find essentially what we now find when we dig up the remnants of Stonehenge, for example, and we say, wow, these people were remarkable ingenious that with their primitive culture, they were able to construct these impressive constructions. But on the other hand, they must have been so extremely naive to believe that, you know, the universe was created at some point and it expanded and that, etc., etc. So I think we should not be we should have the same humility and believe that we will be considered in several millennia from now as primitive or as naive as we are considering other old civilizations for which we are digging up the archaeological remnants right now.
Thank you for this conversation, Nick.
Yeah, you're welcome.
This was a conversation with Nick van der Mortel. I hope you have enjoyed it. This was Back to the Stone Age.